Welcome to rankstudent.com, the site preferred by millions of students around the globe for digital education in science and technology. I'm Dr. Ahmed. I'll be your host for this very important chapter on work, energy, and power. But first, some definitions and some concepts. The vocabulary that's introduced in this chapter includes work, energy, kinetic energy, potential energy, power, elastic and inelastic collisions, and the law of conservation of energy. So what is work? In physics, work is defined as the scalar product of displacement and a force acting in the direction of the displacement. W equals F dot D, which is D times F cosine theta. F dot D is the dot product or the scalar product of the force vector F and displacement vector D. Theta is the angle between the vectors F and D. As an example, work is done in launching a rocket against the gravity of the Earth, as illustrated in the picture on the right-hand side. What is a scalar product? We have studied it in a previous chapter. Let's review it. The scalar product of two vectors A and B is A dot B equals AB cosine theta, where theta, once again, is the angle between the vectors A and B. Since the representation is the dot, it's also called a dot product. The rules governing scalar products, we have studied them in the past. A dot B is the same as B dot A. When you multiply one of the vectors A by a constant quantity lambda, lambda A times B is the same as A times lambda B, which is the same as lambda times AB. The dot product of a unit vector by itself is unity. The dot product of a unit vector with another vector which is perpendicular to it is 0. A dot B is equal to AX BXI plus AY BYJ plus AZ BZK, which means when you take the dot product of two vectors, the components of the two vectors A and B in the X, Y, and Z direction individually multiply. The magnitude A squared is given by the sum of the squares of the magnitudes in each of the individual directions. A squared equals AX squared plus AY squared plus AZ squared. So if you're interested in A, you take the square root of the sum of the squares of the magnitude in each of the three directions. Now, if the force is variable, as illustrated in the diagram on the right-hand side, then the work W is obtained by integrating the force with respect to x. W equals integral of fx dx between xi and xf. That's the area under the curve. No work is done if the force is perpendicular to the displacement. Now, work can be positive or negative because theta can be positive and negative as we rotate around the circle from theta equals 0 to theta equals 360 degrees. We know that between theta equals 0 and 90 degrees, cosine theta is positive, but between 90 and 120 degrees, cosine theta is negative, and therefore the work is negative. By definition, kinetic energy equals 1/2 of mv squared, where v is the velocity. Work and energy have the same dimensions. For a variable force Fx, the change in kinetic energy is obtained by integration of Fx with respect to dx. The final kinetic energy minus the initial kinetic energy equals the integral of Fx dx from xi to xf. This is also called the work-energy theorem. Potential energy is energy stored in a body when work is done against the forces on the body and it's stored up by constraints. V sub F, the potential energy final position, minus V sub I in the initial position, is equal to the integral of Fx dx between xi and xf. Examples: bow and arrow. When you stretch a bow, you are storing potential energy in the bow. When you let go, it is transmitted to the kinetic energy of the arrow. A coiled spring, when you push it down, you store up potential energy. When you let go of it, it springs back. A body lifted up against gravity, such as a rocket being launched into space. In the diagram on the right hand side, you have a pendulum as it swings back and forth in the extreme position, as is illustrated in the diagram. You have potential energy, which gets converted into kinetic energy when the pendulum springs to the vertical position. Work, potential energy, and kinetic energy are interconvertible and have the same dimensions, and the dimensions are m L squared t to the minus 2. When a body is moved against a conservative force Fx, the potential energy is delta V equals minus Fx dx. The potential energy depends only on its final position and not on the path that it takes to get to that position. It does not matter how you move a stone from position A to position B. It's only the location of position B that determines its potential energy. For a body of mass m thrown up in the air to a height h, we can equate the kinetic energy to the potential energy mgh, which is 1/2 of mv squared when the potential energy gets converted into kinetic energy. It's the same situation in a spring mass system. The law of conservation of energy. The total energy in a closed system is conserved. What is a closed system? It is one where the net external force acting on it is zero. A system is considered closed if the forces acting on it are conservative. When a ball is thrown up in the air, the total energy of the ball at every point in the trajectory is the same. E equals k plus v equals constant, illustrated in the diagram on the right hand side. At the top, when v equals 0, it's all potential energy. At the bottom, when v is the final velocity v sub f, it is all kinetic energy. At an intermediate point, where v is v sub h, we have both kinetic and potential energies. However, the sum of the two at each of the three positions is constant. As an illustration again, for a body dropped from a height capital H, mg capital H equals mg small h plus 1/2 of mh squared vh squared plus 1/2 of mv sub f squared, where h is an intermediate point and v sub f is the final velocity. A statement of the fact that the total energy of the body from the initial to the final position and at every point which is intermediate between the initial and the final locations, it is the same. It is conserved. Similarly, the energy of a spring system. When a spring is stretched a distance x, the spring force is given by Hooke's law. Very famous law. You will come across it again and again if you study mechanics. A fundamental law. Fs equals minus Ks. The work done by the force is 1/2 of Kx squared. This work is positive when the spring is stretched in the plus x direction and is negative when the spring is compressed in the minus x direction, illustrated here the top, the spring is stretched in the plus x direction. The bottom, it is compressed in the minus x direction. What happens if you have friction? If there is opposing friction, the work done by the applied force when the spring is stretched to a distance xm is half of kxm squared plus mu mgxm, which is the work that is required to overcome friction. The potential energy is half of kxm squared because the work done in overcoming friction is non-conservative. It is lost. The maximum speed of a spring mass system. If a spring is released from the maximum position xm, the potential energy less the friction is converted into kinetic energy. Stated mathematically, half of mv squared equals 1/2 of kxm squared minus mu times mgxm. This equation can be used to solve for the maximum velocity if xm is known and vice versa. What are the various forms of energy? Heat energy, chemical energy, electrical energy. And Einstein also showed the transformation between mass and energy equals mc squared, one of the most famous equations in all of physics. If heat is absorbed in a process, it is called endothermal. For instance, when you boil water, it absorbs water. It absorbs heat. And the water gets converted into steam. If heat is released, it is called exothermal. Example, burning of wood. Energy is released. These relationships help us solve problems in physics if we know the units, dimensions, and equivalence of the various terms used. For example, 1 BTU equals 778 foot-pounds, which is the same as 252 calories, which is the same as 1054 joules. The law of conservation of energy integrates physics, chemistry, and biology. You can apply it in any of these scientific disciplines. What is power? In physics, power is the rate at which work is done. It is also the rate at which energy is transferred. P equals dW by dt. If a force F, which is a vector, is moved through displacement x, which is another vector, the work done W by the force is W equals F dot x. The incremental work, delta W, equals F dot, the incremental change in position, delta x. Therefore, P equals dW by dt works out to be F dot V, namely the power is the scalar product, the dot product of force and velocity. The units of power are horsepower, watt, kilowatt, foot-pounds per second. They're all used in physics, and it's useful to know their conversions. 1 horsepower is equal to 746 watts, which is the same as 0.746 kilowatts, which is equal to 550 foot-pounds. And energy of 1 kilowatt hours is 1,000 watt hours. This is how you receive your electricity bill in kilowatt hours, which is equal to 3.6 times 10 to the power 6 joules. Collisions are very common. You see them all the time on the road when two cars smash into each other. Collisions can be elastic, inelastic, or partially elastic. In elastic collisions, the colliding bodies spring back. The laws of conservation of momentum and conservation of energy apply. In inelastic collisions, the colliding bodies do not spring back. The law of conservation of momentum still applies. but some energy remains in the colliding bodies due to their deformations. The total kinetic energy after collision is less than the total kinetic energy before the collision because some of it stays in the deformed bodies. In an elastic collision, the conservation of momentum, the initial momentum of body 1 plus the initial momentum of body 2 is equal to the final momentum of body 1 plus the final momentum of body 2. Similarly, the conservation of energy. In a completely inelastic collision, the conservation of momentum is the same, but the loss in kinetic energy is given by 1/2 of m1 v1 I squared plus 1/2 of m2 v2 I squared minus 1/2 of m1 plus m2 v sub f squared. This is stored in the deformed bodies. Now, we have gone over a great deal in terms of force, work, energy, kinetic energy, potential energy. We learn by listening and doing. Merely listening is not sufficient. We must do and solve practical problems. It is important to practice with actual examples from previous NEET, JEE, board exams, or any other tests that your board has prescribed. I recommend that you log on to www.rankstudent.com, download almost 40,000 to 100,000 questions that we have come up with, the answers and the answer elaborations. Take advantage of them and practice often. Practice will help solidify the concepts. Without practice, it is difficult to be a good physicist. It is difficult to know what physics is, difficult to be a good scientist. Science is based on empiricism. It is based on doing. I thank you for your attention.